This chapter is a continuation of chapter 16 with different terminology for some of the circuits we have already seen. Here is a non-inverting amplifier, but now we're going to call this a voltage-controlled voltage source. We need the information from the data sheet in order to find the input impedance and the total harmonic distortion. First, we find the feedback fraction from the formula shown, and then notice that the gain is simply 1 over B. In other words, 1 over the feedback fraction, which gives us the gain. We combine the information from the data sheet and then the feedback fraction into the input impedance formula, and we see that the input impedance for an op-amp is very high. In this case, 470 megohms. We simply say it's very high. Again, we combine the information from the datasheet with the feedback fraction, and we calculate the total harmonic distortion. And you can see it's very low, which means that the op-amp puts very little noise into a circuit in which it's operating. Here is a current-controlled voltage source where a known input current has been converted into a voltage output. Usually, the input current is known and the output voltage is known, and what remains is to calculate the feedback resistor. This is called a voltage-controlled current source, where a known voltage must create a certain current through the load. Notice that the simple formula says that the current through the load depends on the input voltage and the value of R1, and it doesn't matter the resistance of the load. Here we have a current-controlled current source, also called a current amplifier. The object here is to amplify the current through the load. First, find the current gain, and then once you have the current gain, you can calculate the output current. Notice how high the current gain is. The slew rate is a measure of how fast an amplifier can operate. Let's say that the circuit shown has a gain of 10 and an FU of 1 megahertz. We use FU and the gain to calculate the highest frequency, also known as the corner frequency. We combine the slew rate and then the corner frequency to find the highest amplitude that we can put through the circuit. Usually the slew rate is expressed in volts per microsecond, but in this case we convert it to volts per second to simplify the calculation.